Okay, so we need to move on because x2 in our solution x2 is 3 over 2. So in that case, we need to further split our problem P2 into P4 and P5 by adding two constraints. We add x2 less than or equal to 1 and x2 greater than or equal to 2. Why is that? Because this guy is 1.5. It is within 1 and 2. So we need to eliminate the possibility for this guy to be 1.5. That's why we add these two constraints. Okay? So once we add x2 less than or equal to 1, we get our feasible region here. So don't forget that this is the result of adding two constraints. Okay? Previously, when we are at P2, for P2, we already have this constraint, x1 less than or equal to 2. For P4, we add one additional one. So now our x1 is less than or equal to 2, and the x2 must be less than or equal to 1. In this case, once we solve the linear relaxation, then our x4, the optimal solution, would be 2, 1. This is an integer solution. That's very good. If we add the other side, x2 is greater than or equal to 2, then in this case, we get two constraints. x1 should be less than or equal to 2. Okay, this is this one. And your x2 now should be greater than or equal to 2. So once we do that, the feasible region becomes here, and then our optimal solution is 7 over 4 and 2. Okay, another fractional solution. Putting the information back to our original problem. In this case, we can see that for problem P4, actually we get an integer solution, 2, 1. So x4 satisfies all the integer constraints. So we say it is IP feasible. It is feasible to the original integer program, which is denoted as P0. Okay? So x4 now serves as a candidate solution to the original integer program. It is good, but maybe it is not optimal, because here we have subproblem P5. It is fractional, so we need to do something else to solve P5 to see whether this is going to generate a solution that is even better than x4. Okay, so that's something we need to do. So let's move on. This guy, 7 over 4, is 1 point something. So we add two constraints, x1 less than or equal to 1 and x1 greater than or equal to 2. For the first one, we add a constraint. So now in this program, we have 3 newly added constraints. Again, here, once we do this cut, we're going to get 1 and 7.2 7 over 2. Well, unfortunately, this is fractional again. So later we need to talk about this subproblem. Or if we add x1 should be greater than or equal to 2, then in this case, we're going to see that, oh, we are having, again, an infeasible problem. Because if your x1 is less than or equal to 2, and your x1 is greater than or equal to 2, your x1 must be 2. But then, immediately, that as long as you also have x2 no less than 2, then you are going to have an infeasible solution. So this node, again, is dead. So putting information back, this is done, and also this is done. So pretty much we are reaching an outcome. But here you also may do some observation on our remaining node P6. Okay? The only alive node is subproblem 6, where your x2, 7 over 2, is fractional. But don't forget that when we are going down, when we are going deeper, our objective value would only decrease, right? So if we do further, for example, if we say x2 should be less than or equal to 3, or x2 should be greater than or equal to 4, then in either case, we are not going to get a value that is greater than or equal to 13 over 2. Okay, that's something we mentioned. But you already get a solution that is 7. 7 is already greater than 13 over 2. If you are going to get something that is even smaller, there's no way for them to be optimal. So actually, we may stop here. Once we do this, we see we're going to get a solution worse than that. And also, we know 7 is already good enough. So that's why we say we may stop here, because all the solution that we may generate would be worse than x4. So, or I should say, cannot be greater than or better than x4. So here, there's no need to keep branching on this solution, this problem P6. This is the bounding situation in the branch and bound algorithm. So this algorithm has two words there. Branch is the idea of splitting one problem to two. Bound is to say that once we get a feasible solution, we get 7. 7 provides a bound. 7 is saying that for this maximization problem, 7 is a lower bound, or any feasible solution to the IP gives us a lower bound on your optimal solution. The optimal solution cannot be worse than 7 because 7 is already feasible. Your optimal solution must be better than 7. 7, 8, 9, or whatever. It cannot be worse than 7. So somehow, if you see 13 over 2, you don't need to keep branching. And this lower bound provides us this useful information. So a very quick summary says that once we run the branch and bound algorithm, we maintain a tree. If you really want to write a program to do this, you also need to maintain a tree. You get new nodes, and you get connections by yourself so that you know where you are. If a subproblem is solved, and if the solution is IP feasible, we may set it as a candidate solution. Of course, we do that only if it is currently better than the current candidate. So when we are doing branching, we always keep an eye on the currently best solution. Once we get a better one, we replace the current solution. So we always update the current best solution that we already found, so that we may provide better upper bound, better lower bound, better lower bound, better lower bound. If a subproblem is infeasible, then it is dead. If a subproblem and optimal solution is not IP feasible, then either we keep branching on a fractional solution, or once we can see there's no hope to generate a better one, then we stop. So this branch is the idea of getting all the trials, all the required trials. And this bounding idea is to say we can save our time and not to solve those problems that has no hope to generate an optimal solution. So one is to make sure that our algorithm is correct. The other one is saying that we can speed up our algorithm.